So, hello dear students. So, please mark your attendance along with your roll number and name. So, let us wait for 1 or 2 minutes, then we will start our lecture. So, today we are going to start the relation between statistics and thermodynamics, and in the starting first few minutes I will discuss about the macrostate and microstate of a system, so that we have already discussed in our previous lecture. So let me check how many students. So total 15 students are there. So please mark your attendance before we start our lecture. So we will discuss a quick review about the macrostate and microstate of a system. Then I will give you an example how you can differentiate between this macrostate and microstate of a system, and then we will drive a relation between the statistics and thermodynamics, and how using the help of statistics we can find out the various thermodynamic parameters. So let us start. So macrostates and microstate of a system. Now whenever we talk about a system and we say that the system composed of these number of particles, so which is decomposed for a particular volume, and the total energy of this particle, it is given in form of E. So let us say this system which is having a large number of particles. So the system can compose of any matter. It can be a gas, it can be a liquid, it can be any other form like plasma. So let there are n number of particles which are present in this system, and they are confined to a particular space that is generally represented with the volume of this system. And let us say the total energy of this system, which is composed of the total energy of all these particles. So the number I, it varies from 1 to infinity. So multiply by Ni, that is equal to the total energy that we have described in our previous lecture. So these three physical, or you can say the extensive or intensive parameters, so which are dependent upon the nature of the particle, what type of gas or what type of matter which is present in this system, and that is known as the macrostates of a system. Now if we go inside this system, that is at molecular level, the situation is very complex. So when we go at molecular level, so that is when we are trying to study the interaction of these particulars so with each other. So it is very complex. So here there exists a large number of possibilities via which this energy E can be distributed over large number of particles, so that is n. So we cannot say in practical that the system or the molecule is having this much of energy, so we cannot differentiate that. So for example, so the fraction of these molecules, so they are having energy EI, so here these fraction of molecules, so they are having different energy E2. So it is quite difficult to differentiate how many number of particles so which are having at a particular energy value. So statistical mechanics, so we generally defined so a term that is known as the microstate, so which represents the total number of ways this energy E can be distributed over these n particles. So even though for the classical level we generally consider that the system is non-interacting, so corresponding to a given macrostate, so for a given macrostate there exists a large number of microstates. ਹੁਣ ਜੇ ਮੈਂ ਇਹਦੀ ਗੱਲ ਹੀ ਕਰਾਂ ਕਿ ਸਪੋਜ਼ ਕਰ ਲਓ ਸਿਸਟਮ ਦੇ ਵਿੱਚ 1000 ਜਿਹੜੇ 1000 ਪਾਰਟੀਕਲਸ ਹੈਗੇ ਆ, ਸੋ ਉਸ ਕੇਸ ਦੇ ਵਿੱਚ ਸਪੋਜ਼ ਕਰ ਲਓ ਕਿ ਉਹਨਾਂ ਦੇ ਵਿੱਚੋਂ 100 ਪਾਰਟੀਕਲ ਜਿਹੜੇ ਹੈਗੇ ਆ, ਸੋ ਦੇ ਆਰ interacting with each other, so whose energy is E1, so 50 particles are having some energy E2. so ਇਹ ਹਰ ਇੱਕ ਜਿਹੜੇ ਇਹ ਪਾਰਟੀਕੂਲਰ ਦੇ ਗਰੁੱਪਸ ਦੇ ਵਿੱਚ ਜਿਹੜੇ ਆ ਉਹ ਕਿੱਦਾਂ ਕਿੱਦਾਂ ਆਪਸ ਦੇ ਵਿੱਚ ਇੰਟਰੈਕਟ ਕਰ ਰਹੇ ਆ, so there are a large number of ways so that can be discussed, so by which they are distributing their energy with each other. So each states that how they are exchanging these parameters, so like N, V or E, so how the macrostates they are being exchanged by these particles, so that is generally represented with microstates. So this is the connection. So this is the connection how we can discuss between the microstate and a macrostate. Now let us take an example. Now suppose I have two boxes. Let us say this is box A, this is box B, or you can say let us say this is box X, this is box Y. Now we have to throw 4 particles, so like A, B, C, D, these are our 4 particles, and we have to throw randomly these particles, so these particles are distinguishable. Now there are many following possibility with which these particles so they can be present in these boxes. So the microstates, so if I throw 4 particles, so here I will write macrostate. So for the first case, suppose there is probability that all the 4 particles so they will be present in one box and there is 0 particle that is present in box X. So in that case we can write the microstate as something like 0, or you can say here A, B, C, D. So the frequency for this case, that is 1, and second case there is probability one particle can go in box 1, the other can go in box 2. So in that case, so there is possibility compartment 1 ਦੇ ਵਿੱਚ ਜਿਹੜੇ ਕਿਹੜੇ ਕਿਹੜੇ ਪਾਰਟੀਕਲ ਜਾ ਸਕਦੇ ਆ, ਸਪੋਜ਼ A, B, C, D. So similarly B, C, D, A, C, D, A, B, D in compartment 2 and A, B, C. So here the frequency is total 4 frequency. So you can say that the macrostate over macrostate versus microstate, so the frequency is 1 over 4. So similarly, if two particles, so they are going in each box, so then there is possibility, there are different 6 cases, so I will not go in detail. So there will be large number of microstates. So let us say AB can go in this, CD can go in this, AC can go in this, BD can go in this, AD can go in this, BC can go in this, BC can go in this, AD can go in this, BD can go in first, AC can go in this. So similarly for here, CD can go in this, AB can go in this. So there are large number of microstates so which exist. So total number of microstate, that is 6 number of microstates, while frequency for this case you can say it is of the order of 1 by 6. So therefore there are number of ways so with which these particles can be distributed. So the number of particles in 2 compartments define a distribution or a macrostate. So this define how much particles so they are present in particular states, so that is known as the macrostate, and there are 5 different macrostates so which are present. So 5 different macrostates, they are 0:4, 1:3, 2:2, 3:1 and 4:0. So it is seen that when n distinguishable particles have to be distributed in these 2 particles, so total number of macrostates, so if we have to distribute n number of particles, so in that case total number of macrostates will be n plus 1. So this is how you can calculate the number of macrostates. So the properties of this system, it depend upon the number of particles in each compartment rather than which particular particles are in which compartments. So thus macrostates must be considered while determining the properties of a system. Now for a given macrostate, So there are number of microstates. So this we have already calculated. So like for a distribution of 0:3, so there are 4 microstates. So for 2:2, for a particular macrostates, so there are 6 microstates which are present in this case. So this is how we can discuss these macrostates and microstates. So from that we can derive the thermodynamic probability. So this we will derive in our next lecture. So thermodynamic probability so it again depend upon whether the particles are distinguishable or indistinguishable. So again, classical mechanics treats the particle as distinguishable, while the quantum mechanics, where Heisenberg uncertainty principle, which implies, so it treats the particle as quantum mechanics. So this we will discuss in detail in the third and fourth unit. Now let us discuss about the specification of states. So specification of states means, so we must have a technique to find the number of microstates in the given system. So the number of microstates, so that we can find from the given macrostates. So in order to find this, we must establish a detailed method of describing the states of a system. So what does it means? That we must have a detailed way of describing the exact microstate in which a system can be found. So we must have a detailed way of describing the exact microstates in which a system can be found, as well as you can say a precise, that is the closest way of describing the macrostates of a system. So what does it mean? So for the given macrostates, so for example, if there are N, V and E macrostates which are present in a system, and from these macrostates, which macrostates of the two subsystems, so they are interacting with each other, and through that we can find out the number of ways with which these macrostates they are exchanging their parameters with that subsystems. So For a larger case, so we have to consider the statistical distribution in an ensemble. So ਜੇ ਆਪਾਂ ਗੱਲ ਕਰੀਏ, we must describe this system in terms of an ensemble. So ensemble is the mental copies of one system. So that is known as ensemble, and there are generally three type of ensembles which we will discuss. That is microcanonical, canonical ensemble, and grand canonical ensemble. So let us take an example. So for example, tossing one coin, so उस केस ਦੇ ਵਿੱਚ ਕੀ ਹੋ ਸਕਦਾ, either there can be head or there can be tail. So this is the example of one system. Now if I take, so there are suppose 1 lakh coins, 1 lakh similar coins. So if I tossing these 1 lakh coins at the same time, and then I can finding the probability distribution of the head and tail, then that is known as a ensemble, because now I am talking about a large number of systems, so which are identical, and I am finding the probability distribution of head and tail for this case. So this 1 lakh coin study, that is known as the ensemble. So similarly, when we are talking about the kinetic theory of gases and how these particles, so they are being exchanging their energy, how they are exchanging their chemical potential, how they are exchanging their volume or their temperature. So that is, we are taking the identical particles, so which are present in a large system. So then we will study such type of problems in form of ensemble. So we are not concerned with exact description of the system here, rather we deal with statistical description of what we might expect when each experiment is carried out under similar conditions. So while studying this ensemble, so rather we do not find the exact energy distribution for each particle and how they are exchanging their temperature, how they are exchanging their chemical potential. So but we will find some parameters. So using this statistical description, so we can reach to the closest results which can tell us about the description of that particle, how they are exchanging various physical parameters under similar circumstances. So again, in this statistical ensemble, we will consider the theory of equal a prior probability. So we assume that all of the possible microstates are equally likely. So here in this theory, which is equal a likely probability, some books it has mentioned equal a likely probability. So in this we assume that all the microstates are equally likely. So what does it means? So it means there is no real basis for this assumption. So this is generally a prior assumption of this theory. So this we have assumed that there can be this number of microstates which can be present for this type of systems. So let us say, for if you talk about a coin, so then there is the probability of head and tail that is same. So this represents the equal a prior probability, that is there is the same probability of coming head and there is same probability of coming tail. So similarly, if you throw a dice, so then there is equally likely probability for each phase to come. So there is equal probability that phase 1 will come upside direction. So there is equal probability when we throw a dice, 2 can be on the upside direction. So for each phase, so there is equal probability of 1/6. So they are being explained using this equal a prior probability. Now let us discuss specification of states at classical and quantum mechanically. So specifications of a state, so that is present in system, classical versus quantum state. Now in this we have to see that in which state of a system is actually existing, and we have to analyze that state which is existing. So for this we consider an ensemble of particles, so that is a system containing many similar number of copies of one system. So that is known as the ensemble. Now in quantum mechanics we generally describe a system with a wave function. So using that wave function we can discuss their position coordinate, we can discuss their momentum coordinate, so and so. So what is the wave function at a particular position coordinate with respect to momentum? So that we can generally explain with the degrees of freedom. So while in classical mechanics we generally represent this system with microstates, and using that microstates we find the various thermodynamic parameters. So in classical mechanics we consider the system as particles. So in quantum mechanics we consider, so they are moving in form of waves. So system as waves, while in classical mechanics we consider them as particles, and we find the number of microstates with respect to particular macrostate, and using that microstate we can find the various thermodynamic parameters, we can find the entropy, we can find their temperature, we can find their pressure, we can find their chemical potential, we can find their internal energy, we can find their Helmholtz energy, so and so. So this is how we generally calculate the system classically with respect to quantum mechanical. So let us talk about a classical system. Now how we can explain it in a simple way. Now suppose we have this large park, so you can say a square park. So this side it is representing its position coordinate, so this is representing its momentum coordinate. So how we can, so just a minute, so let me move to some other place. कितने में तक आना है? खोली बुआ